In this video, I would like to show you a very cool method of multiplying polynomials that you may not see in the videos provided by the publisher. This method is called the box method. Let's say you need to multiply two binomials, 2x minus 5 with 3x plus 1. If you apply a typical method presented in any textbook, you're going to use really an expanded version of distribution. You're going to distribute 2x into both terms of the second binomial, and then later you're going to distribute -5 into both terms of the second binomial. We commonly call this method foiling method. Foil for first, outer, inner, and last. It's a way to keep track what multiplies after what. For example, first stands for multiplying 2x times 3x because those terms are first in each binomial. Outer stands for multiplying 2x times +1 because those are the outer terms when you look at the entire product. Inner terms are -5 and 3x. As you can see, they're kind of in the middle of this entire problem. And last are -5 and 1. They're last in each binomial. So if you use this method, the resulting products that you're going to get are the following. 2x times 3x are 6x squared. 2x times +1 is just positive 2x. -5 times positive 3x is -15x. And lastly, -5 times +1 is -5. Now I need to consider whether there is any way to simplify this expression, and there is. I am adding like terms. Both of these terms have x to the first power, and therefore the resulting expression is 6x squared minus 13x minus 5, and that is the product I was looking for. So this method is called foiling method in many cases, or the expanded distribution method. I would like to do this problem using the box method now. So what is this box method about? The idea is that you create a box or table with as many rows and as many columns as you need to represent the terms of each polynomial you multiply. So since I'm multiplying a binomial times binomial, or two-term times two-term expressions, I need a 2x2 box. So let's get it out here. So here's my 2x2 box. You choose which binomial will be responsible for which side. For example, I'm going to say that 2x and -5 will be responsible for columns, and 3x and +1 will be responsible for rows. Now I will be multiplying the corresponding entries and filling in each cell of this box. 3x meets with 2x, but multiplication produces 6x squared. 3x meets -5, that's -15x. 1 meets 2x, 2x. 1 meets -5 gives me -5 back. Look inside of the box. This is the product. And if you notice, I can combine like terms, and when I'm done, the resulting expression will be 6x squared minus 13x minus 5, which is exactly the same thing we got by using the foiling method. If you are a visual learner, you will appreciate this method very much because it helps you to organize your numbers, your expressions, and prevents you from making silly mistakes and losing an x here somewhere or a power somewhere or something like that. It's very beneficial when your problems become larger and more complicated. Let me demonstrate what I mean. Let's say now I need to multiply these two polynomials. They have 3 terms, and doing the foiling process can be time-consuming. You may lose some little details here and there by accident, and keeping track of what you already multiplied and what you didn't may be a challenge. Although many of you may like this method and use it, I don't have no problem with this, but I would like to show you another way by using this box method. Hopefully some of you will appreciate it and make it your own tool of choice. So what would the box method look for this problem? I will need a box that has 3 rows and 3 columns because I have a trinomial in each case. Here it is. I'm creating my playing field here. I am going to write terms of my first trinomial, say above the box. So I have 3x squared responsible for first column, positive 5x, negative 2, so just keep going. The next binomial will be responsible for rows, x squared, 4x, negative 3. Now it's time to fill in this box. As you notice, we will end up with 9 small products that later will have to combine and give me a final result. So let's start filling in these cells. X squared times 3x squared is 3x to the fourth. X squared times 5x is 5x to the third. X squared times negative 2, negative 2x squared. 4x times 3x squared, 12x to the third. 4x times 5x, 20x squared. 4x times negative 2, negative 8x. Last row. Negative 9x squared is the result of negative 3 times 3x squared, so negative 9x squared. Negative 3 times 5x is negative 15x. And finally, negative 3 times negative 2 is 6. I hope you agree that having this visual format really helps to keep track of products, the exponents you get when you multiply, the signs of the products in a much easier way. At least that's how I feel about it. But I'm a visual learner, so any visual aid is always better for me than having none. All right, so let's take a look inside of this box. Everything that you see in blue is my product, but there are 9 terms, and I see that there are a lot of ways for me to make this much simpler. For example, my first term, 3x to the fourth, has no other like terms to work with it. So I'm just going to write down 3x to the fourth is my first term, my product. Please notice that the 12x to the third and 5x to the third are like terms. Let's add them together and get 17x to the third. Then along the next diagonal, I see all the x squareds. So let's combine them and see what we get. Negative 9 plus 20 is positive 11. And minus 2, that's a positive 9. So I have a total of 9x squared plus 9x squared. Therefore, I write it here. That's this diagonal taken care of. Lastly, negative 15x and another negative 8x. That's another pair of like terms, and that gives me negative 23x. And finally, plus 6 is my constant. So my product is this expression. I really believe that using box method is an easier way of handling problems like this. So if you are in favor of this method, you are welcome to use it when you do products of polynomials.